think I'm recording here. So let's go to camera, make sure I'm looking at the right stuff here. This whole thing is bizarre, this pandemic and online teaching. Personally, I don't think it's very fun. So you may notice that in some of my videos, right, I'm downstairs in a t-shirt, hanging out, short hair. Because it was summertime and it was warm in my basement office. And now I'm in my basement office, but it's winter. We just got a bunch of snow. But it's cold down here, so I'm wearing a hat and a hoodie, and I'm trying to be comfortable. So anyway, my previous lecture on stress concentrations I don't think was very good, so I'm going to redo that. And so here we go. It's stress concentrations. Now, this is a complicated topic. We're just going to cover the stuff that we really need. All right, first a couple housekeeping things. These lecture slides are based on, I kind of picked and choose images and equations and stuff from different books, right? So you can't necessarily use a variable name for variable name and equation for equation, and you can't take. You just have to be careful, pay attention, right? We'll get much more into that later, reference your book. Your book is consistent with itself. Juvenile is consistent, even with the different editions. Juvenile is consistent with itself. The homework numbering and the chapter numbers aren't necessarily. But you've got to read the book. Secondly, these I'm gonna go back to this part here. The lectures are not intended to just mimic the book. As I've said, before the printing press, there's only one way to convey information, right? Old guy stands up, talks, students write it down. Right now we've got better options. We have books and we have the internet. It seems like a waste of my time and a waste of your time for me to sit here and talk at you and give you exactly the same stuff that's in the book. So I'm not going to do that. What I'm going to give you is some insight, some compliments, not compliments like, oh, your hair looks great, but I'm going to take the information in the book and complement it with what I do, so you kind of get multiple views of the same topic, right? So you need to watch the lectures, and I'm going to try to add to, elaborate on, explain what's in the book, but you need to read the book to do that. So anyway, that's that. And then what was the other thing here? Housekeeping. Oh yeah, don't machine wash it. Yeah, whatever. That was a dumb mistake. Well, it was a $110 mistake, but don't do it. So, stress concentrations. Now, you've done this in 307, right? It's too much work for one credit. So I'm not going to spend a ton of time talking about these. The moral of the story is that I've got some sigma nom, right? Some nominal stress here, and that's simply what you learned in 306. It's the load divided by the area, right? But the thing is, stress flows, right? Stress diffuses, strain diffuses, just like anything else. So if I've got a bunch of lines of force going through here, and I go down here, it's like, whoop, this has to go somewhere, so it goes up and around. And this has to go somewhere, and it goes up and around. And so if you imagine these to be streamlines, like from fluids class, right, there's a lot more, there's a lot more action going on here and here than there is everywhere else. So if the strain is concentrated, the stress also gets concentrated. So right along the sides there are stress. Back in the day, this had to be all done experimentally, but now we've got computer models that can do it. So we can make a model of this simple hole in the plate and discover what the strains actually are, the nominal strains and the concentrated strain. Key idea down here. And oh, by the way, there's something going on with the aspect ratio of my iPad and the aspect ratio of YouTube and something. So maybe this doesn't show up on the bottom of your screen on the YouTube version. I don't know what to do about that other than say sorry. I wonder if I can zoom out. No, that didn't work. I can't. Something's going on here. Well, whatever. All right. So based on all these empirical data, we have plots for the theoretical, and the T here stands for theoretical. Oh, come on. Theoretical. And this is, the K is just for a factor. Right, we'll talk about why that is more later. So if we have some geometry, say like a bar with a notch in it, like this one here, we have to know a bunch of things, right? Well, we need to know the cross-sectional area, right? We get that from, the minimal cross-section area is actually right here. and right there. So that's the area we use. But then we have to know how extreme is the stress concentration. And that comes from some other ratios, such as H over H, right? What's the little area compared with the big area? That matters. And then we need to know down here, how big is the hole relative to the size of the bar, right? So we look these things up. We find the appropriate stress concentration factor, wherever that works out to be, and then we multiply that by the nominal stress down here, and then we can get what our maximum concentrated stress is, right? Pretty straightforward. It's just a factor, all right? So here's an example. I think the best way to do this is with an example. We've got, let's see, what do we have? We've got a bar with a hole in it. We're pulling straight on it. Let's give a sense of scale here. 25 millimeters thick. So that's almost an inch, 200 millimeters tall. That's a little over a foot. Is it, or 8 inches? Yeah, so 8 inches tall. And then this thing is, say, I don't know, 16 inches long. This is a big chunk of steel. If you drop this on your foot, you would not walk for a while, right? So for those of you like English units, an inch by 8 inches by a couple feet long, right? This is a big thing. For those who like millimeters, just look at the picture. And then we put 5,000 newtons on it. What's 5,000 newtons? Roughly 1,200 pounds, right? So it's, we're pretty big load on it. We could lift up a small car, or maybe a really big motorcycle, with this bar. So could we do it? I don't know. Well, what are some things we need to know? I need to know the cross-sectional area available, right? And so it's 200 millimeters originally, but I'm going to take away 30, 15, 15, 60. So my height, I'm going to call this height, equals 200 minus 60 is 140 millimeters, and my thickness equals 25 millimeters. My handwriting is terrible because I forgot my little glove. And if I touch my palm to the iPad, even though it supposedly has palm cancellation, it does redo, undo all the time, and it drives me nuts. So my minimum area, the tensile area, or the area available to me, is 3,500 millimeters squared. So 3,500 millimeters squared. And then my load is 5,000, so sigma equals the load divided by the area, so that equals 3,500. Now, remember that a Newton per millimeter squared works out to be a megapascal, and that's very convenient for us. Sigma nominal turns out to be 1.4 megapascals. Let's call it 1.43 newtons per millimeter squared. So that works out to be 1.43 megapascals. And that is my nominal. So I'm going to put a dotted box around that because that's a pretty important intermediate step, right? My nominal stress is 1.43 megapascals. So I've got a piece of steel that has a cross section of 25 by 140 millimeters. That's a big chunk of steel. It'd be heavy to lift. You could lift it, but it'd be heavy. 1.43 megapascals picking up a small car. 1.43 megapascals is nothing in terms of steel, right? So this is a pretty low stress. But we're not looking for a nominal stress. We need concentrated stress. So what is KT? Right, well, let's see, we've got a bar it's got a hole and a notch. All right, so what was that previous one? So here's a bar with a notch. And so before I can find the appropriate stress concentration, I need to know this R over H thing. Okay, what is R over H? R over H is the radius of the notch divided by the minimum width, right? So R over H. And so I'm going to go back here. I'm going to say this is R here, R divided by H. This is H here, right? So that's R over H equals R over H equals the radius is 15 divided by the minimum width there is 140. And so if I did that correctly, R over H works out to be 0.107. So 0.107. Okay, what else do I need? That's R over H, that's part of it. So I got that one, so I'm on this line somewhere. 0.107 is here-ish. All right. And then, boy, I shouldn't have put that there because that's going to screw me up. This thing. And then I need big H over little h. So what's my minimum area versus the nominal area? So that's big H over little h equals 200 divided by 140. And that equals 1.43. All right, so now I go back to here and I go to my 1.43 line. Now, of course, there's not a 1.43 line. I'm going to go, no, I'm just going to leave this here like this. And I'm going to say, I got to follow this. So I'm going to say it's pretty close to the 1.5 line. So I'm just going to go along this line here. You know, a little bit below that. So now I take this line and I go up here and I go about there or so. Right? And it turns out, boy, what figure is this in the book? If you look back in the book, this would give you, let's see, the bar with a notch in it this is figure 4.39. Figure 4.39. So I'm going to write that down. From figure 4.39, KT equals, what is it? I'm looking, it's kind of like right here, maybe a little higher, so 2.55-ish, right? Equals 2.55. Right? Now surely, and this is an important intermediate step here. In fact, I'm going to go do this whole thing. That whole thing is an important intermediate step. Someone now is bothered by this. All right. We're supposed to show our face frequently. Whoop, that's not it. Don't do that. Don't do that. What the heck is that? Stop. No, I don't know what's going on now. So let's do this. That was weird. This whole stress concentration thing is going to bother somebody. Because, but what's the exact answer? I want the formula. What's the exact answer? There isn't, right? Get used to it. This is engineering. So we're going to have to look stuff up. And we're going to have to estimate. We're going to have to make some approximations, right? That's the difference between engineering and science. We've been over this a bunch. So it's very possible, let's look at some other stress concentration factors, that, you found something here, but then, oops, that's not it. That's not it. Yeah, so you got here, and there's stress concentrations between 1 and 3. Here's a bunch more stress concentrations between 1 and 3. Here's a bunch of more stress concentrations between 1 and 7, between 1 and 3. Right? There's lots of different ways to get you could possibly do the totally wrong thing and still stumble upon the right stress concentration. This is dangerous, right? This class is not about getting the right answer. This class is about the right process. So you need to show me what is your process. Because you could be doing the wrong thing to get the right answer, and that's not really right. Secondly, you could take a different approach to something, get a different answer, but as long as you tell me what the process is, I'm okay with that, right? Justify your assumptions, justify what you did, and I'm okay with that answer. So this is a very process-oriented class, not an answer-oriented class. In thermo, you can all get the right answer, right? Do this. There's only one process, and mass balance, energy balance, entropy balance, and you get it right, right? In this class, there's options. So you need to tell me what the process is, and that means tell me where you got, from what figure did you get this KT, and what parameters did you use to get it, all right? So 2.55, which means now that my sigma concentrated equals KT times my sigma nominal, which equals 2.55 times 1.43, and that works out to be, what does that work out to be? I lost my notes. notes come back. Semi-concentrated here is semi-concentrated, 3.64 equals 3.64 megapascals. All right, so that's one of my answers, right? But there's something else to consider, right? That's just for my notch. So this is for the notch, right? I still have to deal with that hole. All right, well, let's see. I need a bar with a hole in it, bar with a hole in it. I don't have a bar with a hole in it. So I keep flipping through the book until I find the one I want. Here's a bar with a hole in it. So that looks more like it. And there's a bar with a hole in it there, though. That's a circled bar. Oh, that's pin loaded. So like if I hang something on a pin that goes through a hole in a piece of steel, right? That gives me kind of this thing. Whereas if I'm just pulling on a piece of steel that has a hole in it, that's different, right? So you got to read the fine print, pay attention to the pictures. And here there's only one line. And so it really only depends on D over B. What is D over B? Diameter of the hole over the maximum width, right? Or the little b, diameter of the hole over maximum width. So D over B equals, we'll call that, boy, I don't know if I should use the 170 or 200. Boy, what do I use here? So I'm going to say that's D over B. What did I do for D over B? So I'm going to use the big one here, just because I'm going to ignore the notch right now, and I'm going to say D over B, which is 30 over the full 200. I honestly don't know if that's right or not, and that D over B gives me a value of 0.15. Right? And then so I go to this one, and I say it only depends on 0.15, so it's here. And that goes to there, and then it looks like it's about 2.5. So it's about the same, right? So from, what figure is that? 4.40. You got to tell me where you got this number. Don't just write down some stuff. KT is about 2.5. And then so that, well, that's less than this one. So this is my critical stress is going to be 3.64. Then I put a box around my final answer, and that will get me full credit. Now this is pretty darn sloppy, but I'm trying to write without putting my hand on the iPad, so sorry about that. All right. So that's basically how you do these things, all right? Now it gets a little trickier, and this topic is a little confusing. I hope you ask me about this in the drop-in lecture, but we'll see what happens next. Okay, so stress concentrations, we do a bunch of stuff, calculate some parameters based on the geometry, find a concentration factor, multiply it by the nominal, and we're good to go. All right, now let's just ignore them. Aha, yes. So we will just ignore it, right? So at least we're going to ignore them for static loading with a ductile material, right? Most materials we use, steel, aluminum, are pretty ductile, right? Some that we use, cast iron, titanium, some really hardened steels, are not very ductile. Why does it make a difference, right? So let's say I've got some unnotched specimen here, right? And it's got this width, and I put some load F. Sometimes load is L, sometimes load is P, sometimes load is F, right? You have to look at the picture, read, take everything in context. And then here I also have the same width, right? The same distance here, right? And the same distance here. So this distance is the same. So I have the same nominal area, the same cross-sectional area. So if I load it up with enough stress to get to the yield strength, right? I'm going to load it up just up until it yields, right? So whatever area works out to be, I want it to just barely yield. In other words, the force is the area times the yield stress, your yield strength. So I just get this thing to yield. On this one over here, however, yeah, that's my nominal stress, but I've got this stress concentration. So over here, it's going to go way up like this, right? So I'm going to have a really high stress right next to that notch. But wait a minute, remember 307? Too much room for one credit, right? What happens, right? Once I get up to my yield stress, what happens? It starts yielding. It doesn't carry any more load. I can't put that much stress on it, which means I can't put that much force on it. And if I can't put that much force on it, what happens? Well, this starts to stretch, this outer fiber starts to stretch, and then so the inner fibers, the fibers next to it, pick up some of the load, right? So I've got a really high stress here where it's yielded, and then low stress in the middle, and then so something goofy happens there. Well, the next thing that happens is so these stretch, so the fibers next to it pick up some of the load, and then the stress distribution looks like this. And then those start to yield, so the ones next to it pick up some of the load, until eventually, right, all the fibers are kind of sharing what they can, right? Now, I'm going to talk more about this more in the residuals with a simpler example that hopefully will make sense, right? So with a ductile material, these start, the fibers, and if we can refer to metal in terms of fibers, the fibers stretch, and then they share the load with the fibers next to them until we have a nice uniform, you might even call it socialist approach to sharing the load, right? The fibers that can take it, and the ones that are suffer the stress concentration, hand off some of the stress. All right. So that's for a static loading on a ductile material. We can just ignore the stress concentrations, right? The stress is just going to go somewhere else. For a brittle material or in a fatigue loading, a repeated loading, that's not the case. So ductile static loading with a stress concentration. All right. The highest stress fibers will yield, right? And then there's load sharing. The fibers right next to the notch will get cold worked. I don't know if you talked about that in 306 much. We're not going to talk about it much in here. The part doesn't see damage unless we go all the way up to ultimate strength and a crack forms, right? And so for that reason, stress concentrations are ignored for ductile static loading. All right, but what about brittle material? All right, so let's draw a brittle material with a notch in it, like that, and then we're going to pull on it like this, pull on it like this. So what does the stress look like? So I'm going to draw a cross section here. Right, what does the stress look like right there? Well, what the stress concentration will look like, it's going to be really high here, and then goes down, and then goes up like that. And say this is, I'm going to do this in, I don't know, black. I'm kind of running out of interesting colors to use here. Let's say this is my strength sub yield, but for a brittle material, strength sub yield might also be the ultimate strength. So what happens? It's not just going to stretch. Brittle materials don't stretch. A crack forms. So now it looks like this. So I've got this same original shape, but I've exceeded the ultimate stress, which is the yield stress, which is the stress at which it cracks. So now I've got a crack that forms here. Crack that forms there, and that's a crack. Right, so now I've got a crazy high. I've got less area. Right, I've got less area now and a crazy high stress concentration from that really sharp crack. So now my new stress concentration at that same section, the sound effects are important. Right, I've lost some area, so now I got to go back to my red to be consistent here. And I've got a crazy high stress there, which means it's going to crack even more. And then this whole, right, then the whole thing breaks, right, boom. It breaks. So if you've got a brittle material, stress concentrations, that's why drilling holes in a heavily loaded cast iron part almost always results in bad things, right? So stress concentrations in a brittle material are a big deal. So this whole topic, is kind of called something. Let me get a different marker here. It's called fracture mechanics, and you can take a whole class in fracture mechanics. It's pretty cool, right? You get into crystals and the shape of the crystals and the size of the crystals and all this stuff. I don't know much about it. It's just not my thing. So I tend to avoid making stuff out of brittle materials. All right, so that's a brittle material. So, we talked about this a little bit before, stress flows, right? If you take an advanced heat transfer class, a computational fluid dynamics class, if you take a advanced, plasticity or elasticity or materials, like instead of ME 306, you take ME 706, you discover that the heat transfer and the fluid mechanics and the stress and strain all follow the same basic diffusion equations, so it flows, right? And so you imagine if I just round out this corner here a little bit. So if I round out the corner a little bit, make it nice and smooth there, make it a smooth corner. Smooth corner gives me a smooth flow. Right? So I don't have a bunch of, kind of lines of force or lines of stress or isostresses, getting jammed on top of each other, right? So here, sharp corner, right, that's bad. Right? So the question is, why don't we just all do that? Why not always do this? Why not do that every time? Well, oftentimes when we have a step or a shoulder or something like that, it's because it has to fit against something, such as a bearing, right? So if I leave this sharp corner here, right, that's bad. So I want to smooth things out, but I want it to be smooth, yet have a nice geometry. Right, I want the geometry to fit up against the bearing or against the other shaft or the collar or whatever. So there's a bunch of ways you can do that, right? But you have to have a flat surface on which to mount the bearing, and a smooth corner through which the stress can flow. All right, so this is just some ways to get around, the fact that ideal geometry always doesn't match up with ideal stress distributions. All right, so that's that. Oh, and that's it. Okay. So that's the end of my story about stress concentrations. Hopefully that elaborated a little bit on what you did in 307. Too much work for one credit. So yeah, that's it. And then what happens when we load something with a stress concentration and then we unload it, right? And some of the stuff is stretched in there, but then we let it shrink back, and then we wind up with compression in some places and tension in other places. We all end up with some residual stresses. We'll talk about that next. Actually, last summer, but next. All right.